Have you ever seen a rusty nail? Or watched a campfire burn brightly? If you have, then you have seen a redox reaction in action. It sounds like a big, complicated word, but it is really just about one thing: electrons moving around. Think of electrons as tiny, tiny particles that are part of every atom. In some chemical reactions, these little electrons decide to jump from one atom to another. When that happens, we call it a redox reaction. It is a fundamental process that happens all around us, from the batteries in your remote control to the way your own body gets energy from food. It is all about the dance of electrons. So, why the name redox? It is actually two words smooshed together: reduction and oxidation. We will get into what those mean in just a bit. For now, just remember that you cannot have one without the other. It is like a seesaw. If one side goes up, the other side must go down. In a redox reaction, if one substance loses electrons, another substance must gain them. There is no in-between. This transfer of electrons is what powers so many things in our world. Chemistry is all about how atoms and molecules interact, and the movement of electrons is one of the most important interactions of all. Let's think about a simple example. When you light a piece of magnesium ribbon, it burns with a super bright white light. What is happening there? The magnesium atoms are giving away their electrons to oxygen atoms from the air. The magnesium changes and the oxygen changes. This movement of electrons releases a whole lot of energy in the form of light and heat. That is a redox reaction. You are not just burning something, you are witnessing a high-speed exchange of electrons between different types of atoms. It is a beautiful and powerful display of chemistry at work, right before your very eyes. Understanding this electron swap is the key to unlocking a huge part of chemistry. It helps us understand how batteries generate electricity, why some metals corrode and others do not, and even how plants use sunlight to make their own food through photosynthesis. It might seem like a small detail, but this electron transfer is a big deal. It governs the flow of energy and the transformation of matter. So the next time you see something rusting or a fire burning, you can say, "Hey, I know what that is. That is a redox reaction." And you'll be absolutely right. Science is all around us. Now let's break down that redox word. It stands for reduction and oxidation. These are the two parts of our electron swapping story. Let's start with oxidation. A simple way to remember it is with the phrase, oxidation is loss of electrons. When an atom or a molecule is oxidized, it loses one or more of its electrons. Its overall electrical charge becomes more positive. Think of it like losing a tiny, negatively charged balloon. If you let go of a negative balloon, you become a little more positive, right? That is exactly what happens to an atom during oxidation. It is the giving part of the electron exchange. On the other side of the coin, we have reduction. You can remember this one with the phrase, reduction is gain of electrons. When an atom or molecule is reduced, it gains one or more electrons. Since electrons are negatively charged, gaining them makes the atom's overall charge more negative or reduced. It is like someone handing you one of those negatively charged balloons. Now you are carrying that extra negative charge, so your overall charge goes down. Reduction is the receiving part of the electron exchange. An atom cannot be reduced unless another atom is there to give up its electrons through oxidation. So, how can you spot these two processes in a chemical equation? You need to look at the oxidation states or oxidation numbers of the atoms. These numbers are like little labels that help us keep track of the electrons. If an atom's oxidation number goes up, becomes more positive, it has been oxidized. For example, if an iron atom with a charge of 0 turns into an iron ion with a charge of +3, it lost 3 electrons. It was oxidized. This simple tracking method is essential for identifying the key players in any redox reaction. Conversely, if an atom's oxidation number goes down, becomes more negative, it has been reduced. Let's say a copper ion with a charge of +2 gains 2 electrons to become a neutral copper atom with a charge of 0. Its oxidation number went from +2 down to 0. It was reduced. Remember, oxidation and reduction are partners in crime. They always, always, always happen together. One substance gets oxidized, and another gets reduced. It is a perfect balance, a chemical give and take that makes the world go round. Okay, science fans, are you ready to balance some redox reactions? It can look tricky at first, but if we follow a set of steps, it becomes much, much easier. The most common way to do this is called the half reaction method. The first step is to split the main reaction into 2 smaller pieces, the oxidation half reaction and the reduction half reaction. You identify which atom is losing electrons and which is gaining them, and you write a separate equation for each process. This helps you focus on one thing at a time, which is a great strategy for solving any science problem. It is much easier than trying to balance everything all at once. Once you have your two half reactions, the next step is to balance all the atoms that are not oxygen or hydrogen. If you have two chromium atoms on one side and only one on the other, you need to add a coefficient to make them equal. After those atoms are balanced, you move on to balancing the oxygen atoms. How do you do that? You add water molecules to the side that needs more oxygen. For every one oxygen atom you need, you add one water molecule. This is a crucial step, especially for reactions happening in a water-based or aqueous solution. Now that your oxygens are balanced, you probably have a new problem. You have added a bunch of hydrogen atoms with your water molecules. So the next step is to balance the hydrogens. You do this by adding hydrogen ions to the side that is missing hydrogen. For every hydrogen atom you need, you add one hydrogen ion. At this point, all the atoms in your half reaction should be balanced. But we are not done yet. We are dealing with redox reactions, so we have to think about the electrons and the electrical charges. This is the most important part of the entire process. The final step for balancing each half reaction is to balance the total electrical charge on both sides of the arrow. You do this by adding electrons, which are negative, to the more positive side of the equation. Count up the total charge on the left and the total charge on the right. Then, add just enough electrons to one side to make the charges on both sides equal. You will add electrons to the product side for oxidation and to the reactant side for reduction. After both half reactions are balanced, you might need to multiply them by small whole numbers to make the number of electrons equal in both. Then, you can add them back together and cancel out anything that appears on both sides. Consider it done. Now that method we just talked about works perfectly for reactions happening in an acidic solution. Why? Because acidic solutions have plenty of extra hydrogen ions floating around, so it makes sense that we can use them to balance our equations. But what if the reaction is happening in a basic or alkaline solution? Basic solutions do not have a lot of hydrogen ions. Instead, they have a lot of hydroxide ions. So we need to adjust our method just a little bit. It is not a whole new set of rules, just one extra step at the end. Here is the trick for balancing in a basic solution. First, you balance the entire equation just like you would for an acidic solution, using water and hydrogen ions. Follow all the steps exactly as we discussed before. When you get to the very end and you have your final balanced equation, look for any hydrogen ions. For every hydrogen ion you see in your final equation, you must add one hydroxide ion to both sides of the equation. Remember, you have to add it to both sides to keep things balanced, just like in algebra. It is a simple but vital modification for these types of chemical environments. When you add hydroxide ions to the side that has hydrogen ions, the hydrogen and hydroxide ions will combine to form water. So, you will end up with water molecules on one side. You might also have water molecules on the other side of the equation already. If that is the case, you can cancel out some of the water molecules, just like you would with any other identical term on both sides of an equation. What you are left with is an equation that is perfectly balanced for a basic solution with hydroxide ions instead of hydrogen ions. It is an elegant way to adapt our method. So, my advice for mastering redox reactions is simple. Practice. Do not just read the steps, try them out. Start with simple equations and work your way up. Write down the steps. Balance atoms, balance oxygen, balance hydrogen, balance charge, and check them off as you go. Use the mnemonic oil rig, which stands for oxidation is loss, reduction is gain, to remember what is happening with the electrons. Chemistry is like building with blocks. The more you practice putting the pieces together, the more confident you will become. You can do this. Science is for everyone, and with these steps, you are well on your way to becoming a redox reaction balancing master. Now that's science.